the time to create a short teaching video on dealing with this idea of the Riemann sum as an integral. Okay, and this showed up on an AP question, and I feel like I just needed to cover it a little bit better. And first off, what is a Riemann sum? It's when you see this little symbol here, which is the Greek letter sigma that stands for sum. And I just want to explain how these things work a little bit better and hopefully make it a little bit easier for you to understand. First off, we know that we can evaluate an integral by finding the area under the curve. And we started this idea by talking about adding up the areas of these rectangles. I have 4 rectangles drawn here on this function f of x. And if you remember, we said we often want to break them up into equal partitions. All right? So we call each of these equal partitions in here the change in x. All right? Delta x. But if I wanted to find the width of one of these, I would take my total width, b minus a, and I would divide it by the number of rectangles that I have. In this case it was 4, but I'm going to put n. And that would be equal to the width of every rectangle. When we think of the delta x, we're thinking of the width of the rectangle. All right? And so, but to find the area of a rectangle, it doesn't matter whether I think, you know, a right or a left. But if I wanted to find the area of this first rectangle, then I needed to do length times width. Well, the width is delta x. The length is the function value, f of x, but let's be more specific. What is this x-coordinate right here? This x-coordinate is actually a plus delta x. So this coordinate right here is actually f of a plus delta x. Okay? And if I were to do this one up here, if I were to do the next rectangle, remember this distance is also delta x. Well, now this would be f of a plus 2 of those delta x. And this one here would be f of a plus 3 of those delta x's. Okay, that would be the actual x-coordinate, a plus 3 of those delta x's. Here it would be a plus 2 of those delta x's. And I really think that's a key to understanding how these Riemann sums are set up, because from that point on, it's just length times width. The length is the function value. The width is always delta x. All right? So when you see some ugly thing, and I'm going to put this on the next screen, like this, the limit as n approaches infinity of this Riemann sum, and they put this little k equals 1, and they put an n up here, and then they put f of a plus delta x times k times delta x. This is what's called a Riemann sum expression for an integral. All right, but I want you to see that we have already talked about what is going on here. This right here is the length. This right here is the width. And if you go back to our picture from the previous page, okay, my width is always delta x, my length is always the function value there, but remember when we break it up into integrals like this, this is 1 delta x, this is 2 delta x's, this is 3 delta x's. And so what they're doing is they're saying this k is representing how many rectangles that we're going to use, okay? And so oftentimes this k is just going to be a 1, okay? But what we're really doing is we're letting the number of rectangles go to infinity. And what that turns into, quite simply, is an integral expression. This whole thing right here becomes the integral. This whole thing becomes f of x, and this becomes dx. All right? And then we somehow have to find out what our limits of integration are. Okay, what is the limits of integration? Well, that comes from the specifics of the problem. I want to go back for a second to this right here. The change in x is equal to the top limit minus the bottom limit divided by n. All right, and so when we looked at this problem yesterday on our practice exam, we ran into this thing, and boy, it looked ugly and it looked painful, but in reality it was actually not as difficult as what you might think it is. So when I have the limit as n approaches infinity, and I've got this Riemann sum, n k equals 1, and then they put this h of negative 1 plus 5k over n, and then they have this 5 over n. Well, it's just a matter of identifying what these pieces are. This thing right here is an integral. All right? This right here is an expression for my delta x. And remember what delta x is. Delta x is b minus a over n. And they even told me that the lower bound is negative 1. And guess what? We see the lower bound right here at negative 1. Remember from our definition, this thing right here, this a, is the lower bound. Okay? So our lower bound is negative 1. Okay? This expression right here, this 5 over n, is my change in x. So all I need to do is make a replacement here. I need to put 5 over n right here. And it's b minus my lower bound, which we found out is negative 1 over n. So my denominators are the same, so I can set the numerators equal to each other. 5 equals b plus 1. Okay, so b has to equal 4. And guess what that is? That's the top limit of integration. Okay, and so this thing right here is just my dx in my expression. And what about this thing over here? Well, remember, let's go back. It's the lower bound plus delta x times k. Well, my delta x is 5 over n. Okay, remember it's b minus a over n times k. All right, and we're even told that k is 1. So if I replace this k with the 1, what I've got here is just h of x, like we said before, that this whole thing right here just turns into the function. And so look what I'm asked to do. I only need to find what is the integral from negative 1 to 4 of h of x dx. And yesterday they gave us, I'm going to pull the problem here, the stem of the problem, paste it. Make it a little bit smaller so I have some room. Alright, so here is h of x, and I'm supposed to find the integral from -1 to 1, 2, 3, 4. So all I really need to do then is calculate these areas. I've got an area, got an area here, I've got an area in here, and I've got a little area there. And by the way, yes, this value is what you think it is. You can do the calculation with your slope, but this value right here is 1/2. So if I want to calculate the integral from -1 to 4 of h of x dx, I just add up the areas. This first area is 1/2. The next area is a negative value. It is -7/4. And the last area right here is 1/4. Okay, just doing base times height divided by 2. That's all I'm doing. And when you add all of those up, you get -1. And we have taken this really ugly, oops, my Mimeo did some extra things that I didn't ask it to do. Sorry about that. The Mimeo pen kind of goes crazy sometimes. Let me fix this. This was h of x dx. So if we go back to this ugly thing, all we had to do was turn it into the integral from -1 to 4. Now, we had a little bit of calculation work to do to find this 4. But it was recognizing this Riemann sum expression, seeing that this thing was just the lower bound, plus my delta x, which changes into just the function. This thing right here is just the dx. And then we had to do our calculation work from b minus a over n to find this top limit. But from that point on, then it's just a straight area. And so hopefully that helps you understand Riemann sums a little bit better. It really comes down to understanding this graph, okay? And being able to understand that it's just a length times a width, and we're adding up. We are just adding up areas, okay? And that's where we wind up with this ugly Riemann sum expression, which just turns into a much cleaner integral symbol and integral problem. And we will stop the video there.